Hey everyone, we've talked about conservation of linear momentum. Today let's talk about conservation of angular momentum. Now this goes back to Euler's second law. We know that the sum of moments is equal to the change in angular momentum. What we're saying now with conservation is what happens if the left-hand side is equal to zero. That is, if sum of moments is equal to zero, therefore ddt of h has to equal zero. As we saw with conservation of linear momentum, this means when ddt of it is equal to zero, that means the quantity h is conserved. So h at some time number 1 is going to equal h at some time number 2 if you were able to prove that the sum of moments is equal to zero. Now, we could be talking, when we say that h at time 1, h at time 2, we could be talking about an individual body. We could be talking about a system. So we're going to do an example in a bit with a satellite that will prove this point. Now, before we do that, before we jump in, one thing I want to point out. We know that Euler's second law, if I expand the derivative, we know that this is I omega dot plus omega cross I omega. Now, if it is true, if we can show that the sum of moments is equal to zero, and we wish to apply conservation laws, right? If we're going to say that momentum at one moment is equal to momentum at another moment, understand that really what we're doing is we're saying that this quantity does not change, which is by itself slightly more interesting than linear momentum. If I omega dot plus omega cross I omega is equal to zero, does that necessarily mean that omega dot is equal to zero? We could, for example, we could take this quantity and we could move it to the other side. That would simply make it negative, right? And we could solve for omega dots. So even in the case where there is no external moments, when the sum of moments is equal to zero, understand that you can still end up having some omega dot term, right? We can solve this for omega dot. I can say that omega dot is equal to, I can take the inertia, remember the inertia is a matrix, I can invert the inertia, and it gets multiplied by omega cross I omega, which is not necessarily zero. It would be zero, consider it would be zero if your inertia matrix is symmetric. If your inertia matrix is something that, the terms are all on the diagonals. So let's say it's 2, 2, and 2, and these are all zeros. Okay. Understand, I could rewrite this. This is equal to 2 multiplied by the identity matrix, right? Just scalar multiplication of 2, right? If you put an identity matrix here in between the omega cross I omega, even if there's a 2 on it, right? That just means the 2 comes out to the front, and you're still left with identity. Identity multiplied by omega will be omega, and omega cross omega is 0. Any vector cross itself, right, is going to equal 0. What happens, though, if your inertia matrix is not diagonal only? Or what if it's not symmetric? What if it's not 2, 2, 2? What if it's 1, 2, 3? Okay, even with something as small a change as this, what will happen is that this term will not equal 0, which means even in the absence of moments, even when sum of moments is equal to 0, you can still have some omega dot. Now, here's what's going to happen. Are you able to make claims then about conservation of angular momentum? You still can. There's an interesting thing that happens if you're in this particular scenario where even in the absence of moments, you still get omega dots. Here's what will happen. You will have some body, and I'm going to draw my potato-shaped meteorite or asteroid, whatever it is, let's say at some moment in time. Remember that h, angular momentum, remember it's a vector, right? So there is some vector, and you have angular momentum about this vector. If this body is asymmetric, if the inertia is not just some scalar form of identity, what will happen, let's say that this is time number 1. What will happen is here is the same meteor. At another moment in time, its momentum might be about that axis. So this was time 1 on the left, time 2 on the right. Clearly, these this object, this asteroid, these are spinning, right? These have momentum about different axes at different moments in time. But what is interesting, if sum of moments is equal to 0, the magnitude of the momentum at time number 1 will equal the magnitude of the momentum at time number 2. The direction will not be conserved, but the magnitude will. Now this is a very general case. We're not going to be doing tumbling asteroids in this course, but just be aware, for an actual body, even in the absence of moments, you can still get angular accelerations, but you do get this interesting behavior where the magnitudes end up being constrained. Okay, this is a much more complicated problem, and really this type of problem, as we saw in the previous lecture, we know that we could write differential equations for a system like this, and of course Euler's second law and the omega cross I omega, of course that term is a part of the differential equations. Once the problem becomes very complicated, usually we just do the equations of motion and numerically integrate them, like we did the projectile. This time though, there are some problems, some very specific problems, if we are able to prove that the sum of moments is equal to 0, and if we make assumptions that the inertia is symmetric, such that this tumbling effect does not happen, we can approach some problems as a conservation of angular momentum problem. Now you have a homework coming up where you have to apply conservation of angular momentum. So let me clean this up. Here's the problem I want to look at today. Imagine that you have a satellite, and this satellite has solar panels attached to it. Let's say that these solar panels, they stack together almost like a deck of cards, right? And they can unload and then they can load. So at time number 1, the solar panels are unloaded, which is to say that they're all, they're stretched out. And then at another moment in time, we have brought all the solar panels together, so it's like we have restacked the deck of cards. So really, when I draw one of them here, understand that there's multiple solar panels stacked on top of each other. So all these solar panels are doing is they extend and then they fold back in. And of course, not drawn to scale. That's fine. And this satellite, we can say that this satellite is it's in orbit, or perhaps we have shot it off into deep space. But what we wish to investigate is the effect that just the extension and the folding of the solar panels has on the momentum of the satellite itself. So standard write-up always applies. We know that we need some point in. Okay, there it is. We would do a position vector to it. We would put a body frame on this satellite. So let's say the frame for the satellite, let's say the X is pointed along the length of the solar panels. We can say that the Z is the long axis. So the Y then is Y is going into the board. And let's say that it is currently experiencing some kind of rotation about the Z-axis. So let's lay out just a bit of the information that we have. We're not going to do a full formal write-up, but let's say that omega into A is equal to 0, 0, theta dot. Now, this claim about omega is true in both cases, right? In both cases, the satellite is experiencing a rotation about its z-axis, but the value of theta is going to change. We're gonna see how that all comes out. So this is one bit of information we have, and of course we've generalized it, right? This is not this isn't a specific value. I'm not saying it's like 2 or 5 or 10. What else are we going to say about it? Well, let's say that the body of the satellite itself, IAA, is symmetric. It's going to be the same number about the x and y axes. It would be a different number about the z axis, but that's okay. We can just generalize it. We can just say IXX, IYY, IZZ, 0, 0, 0, 0, 0. Okay. Next thing we could do is we could talk about the panels themselves. We could give bodies, right? We could call each of these out as a particular body. We could say each panel A, B, C, D, E, F. And again, just to make it easy on us for this example, let's say that all of these are exactly the same. Every solar panel is the same mass, same dimension, so same inertia. What other information do we have? Let's go ahead and make the claim that the sum of moments on A about A is equal to 0. This is an important claim. If you can make this claim, if you can prove it, then you can apply conservation of angular momentum. You have to be able to justify this though. So can we justify it for this system, for this body? Well, what would make these solar panels fold? There has to be some kind of actuator, right, acting on these solar panels, some motor. What we can say is that because of Newton's third law, if any motor acts, let's say on A, if there's some force on A, then there has to be some reaction force pushing back, right? And those forces are actually acting at the same locations. Let's say there's little locations where the motors are mounted. Because there's a reaction force, right? Because there's a match pushing back, then the sum of moments about the center of A is going to equal 0. You're going to have force pushing one way, you're going to have force pushing the other way, and the moment arm is the same. So for objects that are out in space, this one is a fairly easy claim to come up with, as long as when we talk about the angular momentum, and I'm just going to do it for the drawing on the right, understand that the system that we're talking about includes the whole thing. It includes the satellite and the solar panels. So the sum of moments on the whole system then is going to be equal to 0, and we're going to analyze the angular momentum of the whole system. Again, they're rigidly attached, right? They all rotate together. Okay, we have these claims, and this is fine. We could make the same inertia claim about the satellites, right? It's just some known values. Next, let's talk about, before we do the conservation, let's just do angular momentum. We know that h of A about A is going to be the inertia of A about A, omega in A. We could similarly write h of the system about A. And at this point, we all know how to do this. We need all of the bodies. Every body is going to have its momentum, and we want to take all of these momentums about point A. So we're looking at h about A about A. Oh, I called that satellite, the solar panel A. You know what? Here we go. We just leave, we do some quick modification. Just leave the solar panels, A, B, C, D, E, F. And we can call the center of the satellite S. Sure, why not? So really, we want the system. Oh, I wrote A again. Gosh, S. There we go. We want the angular momentum of the whole system taken about this point S. So we need the angular momentum of A about S, and the angular momentum of B about S, and C about S, and dot, dot, dot. Okay. And again, you should know how to do this by now, parallel axis theorem, etc. Because there is no moment on the system, and also because we have selected our bodies to be symmetric, right, diagonal, and it's just going to be rotating about that single axis, we're going to claim that the momentum of this system is constant. So when you work these problems, how do you approach it? Do the write-up as we've done, define the momentum. Next, understand that when we say h of the system about s, that is a general expression, right? The terms in that expression, they're always true. We haven't put any numbers into this, they're just general expressions. So we can say h of the system at time number 1 is going to equal h of the system at time s, about point s at time number 2. And again, are we worried about the direction changing? Right now, we're not. We're not worried about any kind of tumble effect on the satellite. Remember that the tumbling comes in either when you have terms that are off the diagonals, or if your 3 diagonal terms are all different. If they are all different, if you have 1, 2, 3 different terms on the diagonal, you can experience some kind of tumble. And we can, you can actually go into MATLAB and you can do some fast testing with linear algebra and let it do the cross product for you, and you can see what comes out. Okay, so we're not concerned about the direction changing. We're saying that it's just going to rotate about z. There is no moments about it, so that we can make this claim. Now, when we make this claim, what are we doing with this claim to solve problems? Most of the problems that you're going to encounter are going to say that theta dot at time 1 is equal to, and they're going to give you a number. They're going to say 5 radians per second. Okay. And then they're going to ask a question, what is theta dot at time number 2? And then you have to solve for it. This would be your unknown. If you look at this equation, ask yourself how many actual equations are inside of this. The h's are vectors, right? These are 3 by 1s, which means you could take this equation and you can actually break it into 3, right? You can break it into 3 scalar equations. Now, are all 3 of the scalar equations useful? Recall, earlier we defined omega. We said omega was 0, 0, theta dot. That means the scalar equations in the x and y directions, right? Body frame, in the x hat a and y hat a directions. They're going to equal 0. So there's nothing really useful or informative about those particular scalar equations. Really, the scalar equation we're interested in is going to be the z. So what would that look like if we expand this? Well, we would have terms like I xx, AA, theta 1 dot at time number 1, plus, and I'm just going to write dot 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 because again, you should know how to write these angular momentums. And even this term, this is just this is an angular momentum about a center of mass, right? You would need to write it using parallel axis theorem about that point. So you write that whole expression. You have IXX AA, and I'm going to highlight this, and I'm going to take note of the fact that the IXX AA is constant. The right-hand side, we would have IXX AA, theta 1, doesn't matter, theta dot at time number 2 plus dot, dot, dot. Okay. And again, this IXXAA, if it's a constant, then it's a constant. So it's the same value here as well, right? So you take whatever information is given to you in the problem, and whatever this number is, right? It appears on both sides. So really then, what is changing in this problem? We have a single equation. We have one scalar equation which means we can only solve for one unknown. In this problem, then, what would be the unknown? We said that theta 1 dot at time number 1, this is given. And then theta 1 dot at time number 2, this is your unknown. Now, what other terms are changing? Your parallel axis theorem is going to change because the position of the solar panels are sliding, right? So the distances between their local centers of masses and point S, those distances are changing. Which means that, you know, inside of this dot, 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 there's some other terms that will change as well. The important point, though, is that everything on the left-hand side is defined. Everything is known at time number 1. And our system has gone through some kind of change in configuration, right? We have changed the position of these solar panels, which means now on the right-hand side, some, not this one, right? This one's constant, but some of the other terms in the dot, 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 some of those terms, the parallel axis theorem terms, will change. But you're able to calculate them, right? Again, if you know all the dimensions and everything, and now we say, oh, well, now they're just here on top of each other, so you take this one, and this is now ABC, and this one is DEF, and you find their parallel axis theorems about the center. You calculate what changes, you put them into the scalar equation, and then you can solve for an unknown theta dot. So what's going to happen? Just by intuition, we can actually look at this problem and we can realize, maybe not the numbers because there's no numbers here, but we can have some intuition about the effects that this is going to have. And this isn't, it's not something I can do on video now. I usually do it as a demo in class. But imagine you're watching the Olympics. And in the Olympics, you're watching a figure skater. And the figure skaters, when they begin, they're going to go into a spin. And here's your figure skater. And their arms are out. And then they start to spin, right? They push themselves into a turn. And then as they are turning, they take their arms and they move their arms up like this over their head. And maybe they bring their legs in too so that their body becomes very narrow. And by making their body very narrow, bringing all of the mass in towards their middle axis, they've actually reduced the numerical value of their inertias. Obviously their mass hasn't changed, but just changing the orientation affects their inertia. And in this orientation, the inertia is less because the mass is not as spread out. And because of that, if, let's say that they're originally spinning at 5 radians per second, when you go through this change in orientation, you will then be moving at 10 radians per second. And again, I'm just making these numbers up, right? But the figure skater will appear that they are accelerating, right? Which in a way they are accelerating. Really what they're doing is they're conserving their momentum. If, in a very simple case, if we say that and let's say we're doing this about the ZZ theta dot T1 equal to IZZ theta dot at time number 2. If your problem simplifies down to just one of these equations, and you're able to calculate the IZZ terms, and one of these is bigger than the other, and you know theta dot at time 1, you simply calculate theta dot at time 2, right? And then this number will change. And if the inertia term has gotten smaller, then the theta dot term has to increase, right? Because the left-hand side is held constant. Okay. I know it seems very easy right now for me to explain this. Understand that these problems, they tend to get not particularly complicated, they just tend to be long because you have to write this expression for the angular momentum of the system. And it could include all kinds of parallel axis theorem and changes in orientation. So when you're working these, start here, right? Do your normal write-up. Start here, write an expression about angular momentum of the system about some point. Make sure that you justify sum of moments is equal to 0. That part's important. If you do not show sum of moments is equal to 0, then your application of the conservation law is not justified. So make sure you can write this expression. Make sure you show that the sum of moments is equal to 0. Sort out in your head ahead of time what in these terms is going to be changing. For example, in this example, it was the position of the solar panels, right? So they were just, sliding in and out. In some of the homework problems, one of your homework problems is effectively this one. I think you have it's a guy standing on a frictionless platform and he has weights in his hands. And he has the weights out and he's spinning and he brings the weights in. And by doing so, he will change his inertia and thus change his angular velocity. There is another problem on the homework where it's a guy holding a disc and he has it in his hands. And the only thing he does is he takes the disc and he takes the disc and he's holding it in his hand and the disc is spinning about this axis that I'm showing. And then he rotates it like this and then spins it upside down. I think he does, it's a 90-degree turn out and then a 180-degree turn upside down. And by doing so, what will happen is you'll actually get changes in angular momentum. In that problem, nothing about the inertia changed, it's just the orientations changed. So be very careful on that one, pay very close attention to the frames. Okay, so I think that's good on conservation of angular momentum. Again, this was a short video, but don't undersell the complexity of this approach. Final comment though, always keep in mind the limited applicability of this method. You can only do it when the sum of moments is equal to 0. In more complicated problems, we end up just doing equations of motion anyway. Okay, best of luck with that homework. This homework honestly, it's gonna suck, but just do your best. Okay, I will see you next time. Best of luck. Ciao.